Chapter 1.1 What is MCP? Imagine you're an English speaker and you need to communicate with people who only speak German, Chinese, French, or Russian. Without a common language, you'd have to learn each of their languages individually, which would be incredibly time-consuming and inefficient. Now, picture a universal translator standing in the middle. You can speak English to the translator, and it can seamlessly relay your message to the German speaker in German, the Chinese speaker in Chinese, and so on. It also translates their replies back to you in English. This translator acts as a single, standardized interface for communication. MCP is essentially that universal translator, but for AI models. AI models, like large language models, have a vast amount of knowledge from their training data. However, their knowledge is static. It doesn't include real-time information. To get current data or perform specific actions, like accessing a database, reading your local files, or connecting to an app like Slack, the AI needs to use external tools. MCP provides a standardized framework that allows any AI model to seamlessly interact with any external tool, resource, or environment. It acts as a universal connector, much like how a USB-C cable standardizes the connection between all sorts of electronic devices. With MCP, different AI systems can talk to various tools without needing a custom-built connection for each one. Chapter 1.2 Why was MCP created? The primary problem that led to the creation of MCP is what's known as the M times N integration problem. The problem: before MCP, connecting AI models to external tools was a messy, custom job. If a company had 3 different AI applications, let's call them M, and wanted them to use 3 different tools, like a database, a local file system, and a calculator, they would potentially need to build 9 separate integrations. M times N equals 3 times 3 equals 9. Each AI would need its own unique code to talk to each tool. This approach is not scalable. Every time you add a new AI model or a new tool, the number of custom connections you need to build grows exponentially. Developers were constantly reinventing the wheel, and tool creators had to support many different incompatible connection methods to work with various AI platforms. The solution: MCP solves this by introducing a standardized layer that sits between the AI models and the tools. Instead of creating M times N direct connections, you now only need to create M plus N connections. Each of the M AI applications learns how to speak MCP just once. Each of the N tools also learns how to speak MCP just once. Now, any AI can instantly communicate with any tool because they all understand the same language. If you have 3 AIs and 3 tools, you only need 6 connections. 3 plus 3 equals 6, instead of 9. This dramatically simplifies the entire ecosystem, making it easier to develop, scale, and maintain AI applications. Chapter 1.3 MCP Architecture Overview. MCP's architecture is built on a familiar client-server model, but the terms are adapted for the AI world. There are 3 key components: the host, the client, and the server. The host. This is the user-facing AI application where the user and the AI interact. Think of it as the app you're using, such as the Claude desktop app, an AI-powered code editor like Cursor, or a custom chatbot. The host is responsible for managing the conversation, capturing your input, and displaying the AI's responses. When the AI needs an external tool, the host initiates the connection. The client. The MCP client is a component that lives inside the host. Its job is to handle the actual communication with the MCP server. While the host decides what needs to be done, for example, I need to look up the weather, the client knows how to speak the MCP language to request that action from the server. It's like the messenger that carries requests and brings back answers. The server. The MCP server is the external service that provides the actual capabilities, the tools, data, or resources the AI wants to use. It's a wrapper around a specific function, like accessing a database or a web API. The server advertises what it can do in a standard format so any client can discover and use its capabilities. A server can run on your local machine or in the cloud. Chapter 1.4 Tools, Resources, and Prompts. An MCP server offers 3 core types of capabilities that it makes available to an AI model. 1. Tools. These are executable actions that the AI can choose to run. Tools are for doing things, performing calculations, calling an external API, or modifying a file. For example, an AI might decide it needs to call a get weather location to answer a user's question. Because tools can have real-world effects, many MCP implementations require the user to approve a tool's use the first time, ensuring the human remains in control. 2. Resources. These are read-only data sources that the AI can query for information. Think of resources as the AI's reference library. They are for knowing things, retrieving the content of a file, looking up information in a knowledge base, or reading data from a database without changing it. Unlike tools, which the AI often decides to use on its own, resources are typically fetched under the control of the host application. For instance, if you tell the AI to use the company handbook to answer my question, the host would fetch that resource. 3. Prompts. These are predefined prompt templates or conversational workflows that can be used to guide the AI's behavior in a specific way. For example, a server could offer a code review prompt. When selected, this prompt provides the AI with a pre-written set of instructions, like, "You are a meticulous code reviewer. Please review the following code." This saves developers from hard-coding these instructions into their apps and allows for complex, multi-step tasks to be standardized and shared. Prompts are typically selected by the user or developer, not by the AI model itself. Section 2. MCP Projects. The following section provides a hands-on look at how MCP can be used to build a variety of powerful AI applications. Here's a breakdown of each project. Project 1. 100% local and private MCP client. This project demonstrates how to build a fully local and private AI agent. Using tools like Llama Index, Ollama for running models locally, and a simple SQL-like database, you can create an AI that connects to a local MCP server. The server exposes tools to add data to and read data from the database. This setup ensures that all your data and interactions remain on your own machine, providing complete privacy. Project 2. MCP-powered Agentic RAG. This project showcases an advanced search system called Agentic Retrieval Augmented Generation, RAG. The system uses an MCP server with 2 tools, one for searching a specialized vector database using Quadrant, and another for performing a general web search using Bright Data. When a user asks a question, the AI agent, hosted in the Cursor IDE, first checks the local database. If the information isn't there, it automatically falls back to searching the web. This agentic behavior allows the AI to intelligently choose the right tool for the job. Project 3. MCP-powered Financial Analyst. Here, you learn to build a multi-agent system that acts as a financial analyst. Using the Crew AI framework, the system consists of 3 specialized agents. 1. Query Parser. Extracts key details like stock symbols and timeframes from a natural language query. 2. Code Writer. Writes Python code to fetch and visualize the requested stock data. 3. Code Executor. Securely runs the code to generate an analysis or a plot. This entire crew is wrapped in an MCP tool, allowing you to ask for complex financial analyses, e.g., plot the year-to-date stock gains for Tesla versus NVIDIA directly from your code editor. Project 4. MCP-powered Voice Agent. This project guides you through creating a voice-controlled AI assistant. The workflow is as follows. 1. Speech to text. The user's spoken query is transcribed into text using Assembly AI. 2. Tool selection. An agent, powered by the Qwen 3 model, accesses an MCP server with tools for querying a SUPA-based database and performing a web search with Firecrawl. 3. Response generation. The agent chooses the appropriate tool, fetches the necessary information, and generates a text response. 4. Text-to-speech. The final response is converted back into speech and delivered to the user. This creates a seamless conversational experience where the AI can intelligently access different data sources based on your spoken commands. Project 5. A unified MCP server with MindsDB. This project demonstrates how to create a single, unified MCP server that can connect to over 200 different data sources. By using MindsDB, which acts as an AI layer on top of databases, you can connect to sources like Gmail, Slack, GitHub, and various SQL databases. MindsDB exposes these connections as tools through its built-in MCP server. This allows you to use a single interface, like the Cursor IDE, to ask natural language questions and get answers from any of your connected data sources. Project 6. MCP-powered shared memory for Claude and Cursor. Developers often use multiple tools, like the Claude desktop app for brainstorming and the Cursor IDE for coding. A common issue is that these tools don't share context. This project solves that by creating a shared memory layer using Zepp's Graffiti, a knowledge graph tool. An MCP server is set up with tools to add information to and search this shared graph. By connecting both Claude and Cursor to this same MCP server, you can have a conversation in Claude, store the key insights in the shared memory, and then immediately access that context from within Cursor, and vice versa. Project 7. MCP-powered RAG over complex documents. Standard RAG systems often struggle with complex documents that contain tables, charts, and images. This project tackles that challenge by using eye-level AI's GroundX, a platform designed for processing complex, real-world documents. You'll build an MCP server with tools to ingest documents into GroundX and perform advanced searches. This allows your AI agent in Cursor to accurately extract information from visually complex PDFs and other documents. Project 8. MCP-powered synthetic data generator. This project shows you how to build a server that can generate realistic, tabular synthetic data. Using Datacebo's Synthetic Data Vault (SDV) library, an MCP server is created with 3 main tools. 1. Generate. Create synthetic data based on a real dataset. 2. Evaluate. Assesses the quality of the synthetic data by comparing it to the original. 3. Visualize. Generates plots to visually compare the distributions of real and synthetic data. This toolkit, accessible from Cursor, is invaluable for tasks where you need more data for model training but have privacy or data scarcity constraints. Project 9. MCP-powered Deep Researcher. Inspired by ChatGPT's deep research features, this project guides you in building a 100% local alternative. It uses a multi-agent system orchestrated by Crew AI. 1. Web Search Agent. Uses the LinkUp platform to perform deep web searches. 2. Research Analyst Agent. Analyzes the search results, verifies facts, and synthesizes the information. 3. Technical Writer Agent. Takes the structured insights from the analyst and crafts a final, coherent response with citations. This powerful research team is bundled into a single MCP tool, allowing you to conduct in-depth research on any topic directly from your development environment. Project 10. MCP-powered RAG over videos. This project explains how to build a system that lets you chat with your videos. Using RAG AI for video processing, you create an MCP server with 3 tools. 1. Ingestion tool. Indexes videos, processing both the visual and audio channels. 2. Query tool. Retrieves relevant segments from the indexed videos based on a text query. 3. Show video tool. Extracts the specific video chunk with start and end times that contains the answer to your query. This enables you to ask questions like, show me the part of the video where the speaker discusses Q3 earnings, and get the exact clip in response. Project 11. MCP-powered Audio Analysis Toolkit. The final project is an audio analysis toolkit powered by Assembly AI. An MCP server provides tools to transcribe audio files and extract a wealth of insights, including a full transcription, a summary of the audio, identification of different speakers, speaker labels, sentiment analysis, positive, negative, neutral, topic detection. The system also allows you to chat with the audio by asking questions about its content. This toolkit can be integrated with hosts like the Claude desktop app, turning it into a powerful tool for analyzing recorded meetings, interviews, and more. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.